Welcome back. This is Calculus 1, Lecture 10, Trigonometric and Inverse Trigonometric Derivatives. Okay, so to start off with, we have previously seen that the derivative of sine of x is equal to cosine of x, and the derivative of cosine of x is equal to negative sine x. Now, just from these two, we can find the derivatives for the remaining four trigonometric functions. That is tangent x, cotangent x, cosecant x, and secant x. Okay, so let's go ahead and we'll start with tangent x. Tangent is defined as sine of x over cosine of x. Okay, so if we're going to go ahead and find the derivative of this, we can actually represent it with these two and then go ahead and use quotient rule. Okay, so our numerator, f of x, is going to be sine of x. Our denominator, g of x, is going to be cosine of x. And just like our identities up there stated, sine of x is equal, the derivative of sine of x is equal to cosine. The derivative of cosine is equal to negative sine. Okay, and then we just put those together in quotient rule fashion. As a reminder, that's f prime times g minus g prime times f, all of it divided by g of x squared. Okay, so we're just plugging in everything into its appropriate spot. We're going to get cosine times cosine minus negative sine times sine, all of it over cosine squared. Those negatives will give us a positive. We'll get cosine squared x plus sine squared x over cosine squared x. Now, if you remember, we have a Pythagorean identity that you may have seen in pre-calc or you've come across before. In general, sine squared theta plus cosine squared theta is equal to 1. Okay, so we can use that to simplify that numerator to just 1. We're going to be left with 1 divided by cosine squared, which is in fact secant squared, because 1 over cosine x is the definition of secant x. Okay? Now, I'll just add to these Pythagorean identities. We actually had 3 of them. If we take this first one, sine squared plus cosine squared is equal to 1, and we divide every term in here by cosine squared, well, sine squared divided by cosine squared is going to give us tangent squared, because sine divided by cosine is tangent. Cosine squared divided by cosine squared will just be 1, and 1 over cosine squared, just as we've seen here, is going to be secant squared. Okay, so that's going to give us our second Pythagorean identity. And if we wanted the third one, we can go back to the original. And now instead of dividing everything by cosine squared, we divide everything by sine squared. So sine squared divided by sine squared is going to be 1. Cosine squared divided by sine squared will be cotangent squared. Okay, so cotangent is cosine over sine. And then 1 divided by sine squared is going to be cosecant squared theta. Okay, so these were our 3 Pythagorean identities. And these will be useful in calculus as well. All right, so the derivative of tangent x is secant squared x. So let's see what's next. Now let's try to do the same thing for cotangent. Like we just said, cotangent is defined as cosine of x over sine of x. If we're going to take the derivative of this, we can again use quotient rule. This time, f of x is equal to cosine x, g of x is equal to sine x, f prime is going to come out to negative sine, g prime is going to come out to cosine. We use our same formula. We plug everything into its appropriate place. We're going to get negative sine times sine minus cosine times cosine. all of it over sine squared. So we'll be left with negative sine squared minus cosine squared over sine squared. If we factor out a negative from the top, we'll get negative parentheses sine squared plus cosine squared. Denominator stays the same. And as we had just shown in our previous example by the Pythagorean identity, this is just 1. So we're left with negative 1 over sine squared, which is going to come out to negative cosecant squared x. All right. So our next one, we're going to try to figure out what the derivative of cosecant of x is. Now, cosecant of x is defined as 1 over sine of x. Now, you could use quotient rule for this. That would absolutely work, even though we don't technically have a function. We just have a constant in the numerator. It would still work, right? But I'm going to choose to represent this instead as sine of x to the negative 1 power and show that we can also figure out this derivative using chain rule. Okay? So, in other words, the derivative of cosecant of x is going to be, now, by power rule on the outside, negative of sine of x raised to negative 2 power times the derivative of the inside, which is cosine of x. Okay? So this results in negative cosine x over sine squared x. We can separate this out. I can put 1 over sine x into its own fraction, multiply that by cosine over sine. Now the advantage of this is that we know, or we have alternative ways of representing both of these in terms of other trig functions. Okay, so 1 over sine of x is just cosecant of x. Cosine of x over sine of x is just cotangent x. Okay, so the derivative of cosecant is negative cosecant x cotangent x. All right, so I thought that was a little bit of a quicker way to go about doing this. And the same thing is going to be true for secant of x. This is defined as 1 over cosine. We can do the same thing. We can represent this as cosine of x raised to negative 1 power. And then when we go to take that derivative, that power is going to come down, subtract 1 from the exponent, get negative cosine of x raised to negative 2 times the derivative of the inside, which is negative sine x. This also becomes a fraction. Sine of x over cosine squared x. We can, again, separate it out in a very similar fashion. 1 over cosine x here, sine x over cosine x over here. 1 over cosine is just secant. Sine over cosine is just tangent. So the derivative of secant of x is secant of x tangent x. Okay, so you can kind of remember that tangent and cotangent will just come out to something squared. Tangent is secant squared, cotangent becomes negative cosecant squared. Cosecant and secant x both show up in their own derivatives. Okay. So here are all of them kind of just listed nicely in a little tabular format. So these are just things you don't have to derive every single time. You can just memorize these identities and use them. They'll be very useful in the course of Calculus 1 and Calculus 2. All right, so let's try applying them in some typical examples that we might see involving chain rule or logarithmic derivatives, the things we've been covering before. So for the first example, it's asking us to derive y is equal to tangent squared of 5x, which you can rewrite as tangent of 5x squared. Okay, and you can already see what I'm doing here with the color. So I'm identifying the outermost function, which is a square. The next layer is the tangent, and the innermost function is 5x. Okay, so we're going to go about doing this in our chain rule process. F of u, the outermost function, is u squared. Its derivative, 2u by power rule. U, that next layer, is just tangent of v, some other function v, right, that we're calling 5x. Okay, so the derivative of tangent of v, as we've just seen, in general, derivative of tangent of x is equal to secant squared of x. So tangent of v, the derivative, is going to become secant squared v. And finally, v itself is 5x. Its derivative by power rule, or you can say constant multiplier rule, is just 5. And then we're going to put them together piece by piece. So derivative in general, y prime is going to be derivative of each layer multiplied. F prime of u times u prime times v prime. And you could say, this is u prime of v, v prime of x if you really wanted to, but it's fine. Okay, so I'm just putting everything in one by one. F prime of u is 2u times u prime times v prime. Now let's put everything into terms of v. 2 tangent v times secant squared v times v prime. And finally, put everything into terms of x. We're going to get 2 tangent 5x times secant squared 5x times 5. We just clean that up a little bit. Combine like terms. We're going to get 10 tangent 5x times secant squared 5x. Okay, so these trigonometric derivatives integrate perfectly nicely with the rest of our rules. Okay. For the next example, derive y is equal to the natural log of cosecant of x squared. Okay, so again, we've got our 3 layers. Our trigonometric function is just somewhere in the middle again. Natural log is the outermost function. Cosecant is the second function. And x squared is the innermost layer. We start with that natural log. Natural log of u is going to become 1 over u when we derive it. U is equal to cosecant of v. U prime will be negative cosecant v cotangent v. Okay, so that's just coming from up here, what we showed before. And finally, v is just equal to x squared. When we derive it, v prime is equal to 2x by power rule. And the same deal as always, we're going to put them together by multiplying all of those derivatives, each of those layers. We put everything in terms of u that we can, then put everything in terms of v, 1 over cosecant v times negative cosecant v cotangent v times v prime. And finally, put everything into terms of x. So wherever we have those v's, we put those x squares. V prime is going to become 2x. Now from here, I've got a cosecant x squared up here, I've got a cosecant x squared down there. I can cancel those and simplify this nicely into negative 2x cotangent of x squared. All right. So that's how it looks when we're applying our trigonometric derivatives. The next thing we have are inverse trigonometric derivatives. So last time we talked about inverse functions and their derivatives. We saw how the natural logarithm, which is the inverse of the exponential, how that one's derivative worked. So trigonometric functions as well have their inverse functions. Now, these were found using something called implicit differentiation, which is something we're going to come back to later on in the course. So it's a little bit more of an advanced technique of differentiation. For now, we can just memorize these identities and use them as we have to. All right, so the derivative with respect to x of arcsine is 1 over the square root of 1 minus x squared. Derivative of arc cosine is very similar, but we've got a negative 1 there. Negative 1 over square root of 1 minus x squared. Derivative of arc tangent, 1 over 1 plus x squared. Derivative of arc cosecant of x, negative 1. Then we've got this absolute value of x term here, square root of x squared minus 1. Okay, so these have become reversed. Derivative of arc secant of x is almost identical to this, but without that negative sign. And finally, derivative of arc cotangent of x is almost identical to arctangent of x, but we've got a negative again. Okay, so these all follow very similar patterns. You can kind of think of these in pairs. Right. So let's see an example. Let's take the derivative of y is equal to arcsine of natural log of x. So here we've just got 2 layers. So these are actually a little bit simpler than what we were just doing with the trig values, or trigonometric derivatives. Okay, so our outer function f of u is just equal to arcsine of u. Its derivative, f prime of u, is going to come out to 1 over the square root of 1 minus u squared. So I'm just applying that with u in place of x. U is equal to natural log of x. Its derivative is 1 over x. For y prime, we just multiply our derivatives together. Derivative of the outer function times derivative of the inner function. Put everything in terms of u. In the next step, we substitute in everything in terms of x. So our u becomes natural log of x. U prime becomes 1 over x, as per our definitions. And then we just clean this up, put this together a little bit more nicely. Natural log of x squared, we can rewrite this with the 2 here, the same way we might write something like sine of x squared as sine squared x. Okay, so that notation works for this as well. And this x is just going to come outside. All right. And for our last example, let's see if we can take the derivative of y equals e raised to the arctangent of x power. So you've got arctangent of x, this entire inverse trig function, as the exponent of e in this case. Okay, let's see how this is going to work. So obviously e is the outer function. Arctangent is the inner function. I should say e to some power is the outer function. E to the u is what we're going to call this. Now, the nice part about e to the u is that when we derive it, it is its own derivative. So f prime of u is nothing more than e to the u. U is arctangent of x. And from our table above, we had that the derivative of arctangent of x is 1 over 1 plus x squared. And that's exactly what we have here. U prime is 1 over 1 plus x squared. We're going to put this together as we always do. F prime of u times u prime. First, we substitute everything into terms of u. Then we put everything in terms of x. E to the arctangent x times 1 over 1 plus x squared. We throw those together in the same fraction, and we are done. Okay, so even though this is a very complicated looking thing, looks like we have an entire word up here as an exponent of e. This is not that bad of a derivative once we do chain rule. All right, so this is just a quick look at how we can use trigonometric and inverse trigonometric derivative rules to solve these problems in connection with chain rule and quotient rule and all these other things that we've been using so far. All right, I hope you found this video helpful. Please remember to like the video and subscribe to the channel if it was, for more content.